So in the previous video, we considered the idea that sometimes our past experience can impair problem solving in the current domain. So if you get fixated on a particular function of a object, or if you get stuck in a particular mental set, depending on the demands of the current problem, that can sometimes mean we're a little bit slower or find it harder to find the solution. However, I think it's really important to make clear that in most situations, our past experience can generally be very useful and help us in finding appropriate solutions to the current problem. And this is particularly the case when we can either use this prior knowledge to solve the current problem, and there's a similarity between the two of them, or we can use problems that we've solved in the past and use this effectively as an analogy. So where we can draw comparisons and similarities between the way that a problem was posed in one environment and see how that might provide a solution to the current problem. Let's see an example of this. So this is a very famous problem that was posed by Dunker that comes by several different names, but we'll call it the radiation problem here. And I want you to imagine that you're a doctor treating a patient with a malignant stomach tumour. You can't operate on the patient because of the severity of the cancer. So we're putting in a constraint here. But unless you destroy the tumour somehow, the patient will die. You could use a high-intensity X-ray to destroy the tumour, but unfortunately the intensity of the X-rays needed to destroy the tumour will also destroy healthy tissue through which the rays must pass. So X-rays of lesser intensity will spare the healthy tissue, but they will be insufficiently powerful to destroy the tumour. And this is kind of a real-life problem that's being posed here, of how is it that you can treat this tumour using laser rays of a sufficient intensity. So what kind of procedure could you employ that will destroy the tumour without also destroying the healthy tissue surrounding the tumour? Just take a minute to think if you can come up with an appropriate solution to that. So at the moment, in trying to come up with a solution to that past problem, some of the things that you might do in your mind is just think about the current circumstances and think about the parameters of the constraints that you get. But it might also be the case that you draw on past knowledge of things that share some sort of similarity with the constraints and the possible solutions. So one thing the researchers have looked at is if you were to give people an analogous problem, so a problem that shares some kind of similarity to this one, but is maybe a little bit easier to solve, and then see how knowledge of the solution to this problem is able to be transferred and applied to the original radiation problem. So in one study by Holyoake, before they gave them the radiation problem, they presented with another easier problem called the military problem. And in this case, it's described as general wishes to capture a fortress located in the centre of a country. You've got many roads that radiate outwards from the fortress. All have been mined, and because they've had mines placed on the road, it means that a small group of men can pass over the roads safely, whereas a large force is going to detonate these mines. So a full-scale attack down one road is impossible. So you want to attack this fortress, you can only send small groups of men down each road. There's many roads that lead into this fortress. What are you going to do? So many people should be able to, after thinking about this for maybe not too long, should come up with a plausible solution that you could send small groups along multiple roads simultaneously. And again, I think the more applied these kind of problems get, that if you're doing this in a, say for example, in a computer game environment and you're looking to attack something, you would be able to see these solutions much easier than maybe when they're posed theoretically. So if I gave you an image of these, you'd probably find it easier again. So the analogy here is that the solution to the radiation problem is to administer low intensity rays from multiple directions simultaneously. So for example, if you look at the image here, we've got multiple rays that are coming in at a slightly different angle of a lower intensity that are passing through different parts of tissue that are not going to cause any damage to this tissue. And this is a real life solution to some of these treatment problems. So in the study by Hollyoak, they looked at the percentage of people that were capable of finding a solution to the radiation problem. So those participants who received the military problem, the convergent solution, and were then given a hint to apply this knowledge to the radiation problem, 75 to 80% of them effectively came up with this solution. So in other words, you're giving them this military problem, you're telling them what the solution is, and you're saying, yeah, we've given you a solution, you should probably apply this or find this analogy and use it to help you solve the radiation problem. 75 to 80% people can get it. Those that received the military problem but didn't get the convergence solution, so they didn't work out exactly what it is, 40 to 50% of those participants were able to still solve the radiation problem. So they're still applying some of the analogy there. Those that received the military problem but were only instructed to memorize it as a story, out of those, 30% solved the radiation problem. And then for those participants that received the radiation problem in isolation on its own, only 10% of these could effectively solve the radiation problem. So if that's you, if you were able to solve it without any hints previously, congrats, you're in that unique 10% there. Okay, let's talk about insight. So insight refers to the experience of suddenly realizing how to solve a problem. So when it sort of pops into your head that, this is the solution that I've been searching for a lot of the time. So we have non-insight problems, can be generally defined by those where you have a pretty clear understanding of your progression towards that solution or the final goal state that you're searching for. So if you're doing a mathematical problem or you're doing something like the Tower of Hanoi task, as you move those disks around, you're pretty aware most of the time of how close you are to reaching that solution that you want. Whereas for insight, for problems that involve insight, these typically require you seeing some sort of novel perspective in order to reach that solution that you want. So one of the kind of classic examples that's given in history is of Archimedes, who was given the task of deciding whether a crown that had been given to the king was made of pure gold or was a mixture of gold and silver or other alloys. And to come up with a solution, he realized that he could put this into water, and by looking at the displacement of the water, you get different results depending on whether it's gold or alloy. And he could use this to check the kind of quality of the crown without damaging or destroying this. And that moment where you come up with or realize this solution involves this kind of eureka moment or this degree of insight that occurs. So some other examples this might be if I gave you a couple of riddles on here. So what goes on 4 legs at dawn, 2 legs at noon, and 3 legs in the evening? Now, as you're thinking about a possible solution to this, it's unlikely that you're feeling that you're kind of progressing towards the goal. It should suddenly at one moment kind of pop out that maybe that's referring, and in this case this was a famous riddle that was given to Oedipus, who realized that it refers to man. So man who as a baby crawls on 4 legs, then walks on 2 legs throughout their adulthood, and 3 legs in their elderly life, so as they're walking with a cane as the 3rd leg. Another riddle is a woman who lived in a small town, married 20 different men in that same town. All of them are still living, and she never divorced any of them, yet she broke no laws. How could she do this? You have a think about the answer for this, and it turns out that she's the parishioner, or she's the reverend of the town who marries them. So she presides over the marriage rather than actually getting married to them. But the key thing here is we're not kind of progressing steadily towards a solution. It generally sort of pops out. And there's some different approaches required in order to sometimes come up with solutions that require insight. So one example that might illustrate this is the mutilated checkerboard. So in this example, you have 64 squares on the board that are initially covered by 32 dominoes. So this is a normal kind of chess or draft board that is presented here, an 8x8. Then 2 squares are removed from each corner. So as we've done it on here, we've just mutilated this checkerboard. The problem that you're given in here is, can the remaining 62 squares be filled by 31 dominoes? Again, this is a great point just to pause the video and have a think if you can come up with a solution to this. So for most people, when you're trying to initially answer this question, what you might do is begin by trying to mentally cover the square with domino pieces. So if you take this kind of 31 and sort of mentally placing them in different locations to see if they would fit up. However, there's, I think, over 700,000 possible permutations of exactly where you could place those domino pieces. It's relatively unmanageable to think about it in this way. The trick here is to try and reformulate the problem so that it becomes more manageable. So in a way, this is also thinking about representing the problem in a different form. So if you look at this carefully, one of the things that you will see is for every domino that you place on there, it always has to cover one white and one black square. So what that means is you could cover the entire board with dominoes if you're going to cut out one white and one black square. But you can't do it if you've just cut out 2 white or 2 black squares, as what has happened in the case here. So we've chopped off those squares at the corner would both be black. The fact that we've cut those off, we know through that representation of the problem that 31 dominoes, there's no way that they can cover this. Okay, another example of in a kind of more everyday life situation that might require a degree of insight is if you watch this situation here and just see if you can work out why this is funny.
kuule kõikidest päevadest nagu reaalselt või?
No mis sa nüüd teed? Plaan on. Jah, mine sinna. Aga nüüd?
Tere, puu. Aitäh.
Okay, so when you give somebody a kind of clip like this, and say for example the problem is for you to work out and understand why that's amusing, most people would probably struggle the first time around watching this to really grasp it. If you pay more attention and you extract the kind of key details, one hint or one thing that you should have realised is that it's a police checkpoint that they're approaching, where the police are breathalyzing the drivers of the cars to make sure they're not over the alcohol limit. So now that you've got that bit of information, can you think why they're finding it amusing? If you still haven't got it, the sort of second hint that should give you insight into this is the fact that the car is a right-hand drive, whereas most of the cars in this country, this is in some Scandinavian country, most countries there are left-hand drive. So the person that they're breathalyzing is actually the passenger and not the driver, hence why they're finding this quite funny. So I've referred to before the idea that we have this sense of kind of progress towards a solution when we're doing non-insight problems, whereas for insight problems the solution just kind of appears suddenly. And one way you can study this was some research that was done by Metcalfe and Weber, and they gave participants problems that either involved algebra, so similar things to the kind of water jar problem, or that they involved insight. And if you look at the graph that's presented on here, so along the y-axis is their perception of warmth. And you can think of warmth as simply meaning what is your feeling of closeness towards having the solution. And the warmer you are, the closer you are to getting that solution. Whereas along the x-axis, we have the time before they finally found the solution. So they know exactly when that was, and then they kind of work backwards from that to plot each of these warmth ratings on there. So in the blue, we have the warmth for algebra over time, and in the red is the warmth for the insight problems over time. And you see, for the algebra problems, as people are getting kind of closer towards the solution, they self-report that, yes, we're getting closer, I'm feeling warmer, feeling like this solution is just about to appear. Whereas for the insight problems, we tend to only get around about sort of 15 seconds before people might feel a little bit kind of closer towards the solution, and then it sort of spikes up towards the end. So in general, they're not really close to that solution until they sort of suddenly finally hit it and have this kind of insight. So there is some research that looks at the people's kind of perceived progress towards solutions depending on whether they're solving algebraic solutions such as the kind of water jar problems, or whether they're doing solutions that require and involve insight, and ones that we keep saying we only have this sort of sudden realization. So some research by Metcalfe and Weber would give participants either problems that involved algebra or insight, and they would record participants' self-ratings of warmth. And this rating of warmth is basically getting them to give an indicator of how warm, how close do you think you are to finding the solution. And they record this every 15 seconds, and then they've plotted on here. So along the x-axis we have the time before the solution was finally arisen, and if you look at in the blue line the sense of warmth for the algebra equations, as participants are getting closer to solving it, there's a kind of linear relationship that exists there, that the closer they get, the more they self-report feeling like they're getting closer. Whereas if you look at the red line, this is when they're solving the insight problems. It's only really right when they've solved the problem that they report this high level of warmth. At around about sort of 15 seconds beforehand, there's a little bit of an increase, but there's still quite a long way. They don't feel like they're kind of necessarily on the path towards solving that equation or that solution. So that's just an indicator of what I've been saying before, that these algebraic solutions you can involve, or you have this perception of progressing towards the solution, whereas for insight problems, the solution just sort of pops out at the last moment. There's also been some work on what can be done to facilitate or increase insight. So you might be thinking, if I'm coming across problems, well, what is the actual precursor? What determines whether I find that solution or not, or if I'm just kind of sitting there sort of pondering for ages? And a few bits of work on this. The first one shows that you can try and facilitate using hints. So in one example here, they gave the two strings problem that we've already seen. So this is where we know that the strings are too far apart for participants to reach to one string or the other. And we used this as an example of functional fixedness earlier. And this was the most kind of insightful but relatively rare solution, was to tie one of the tools that are on the table, tie that onto one of the bit of the string and swing it across. Now, in some research by Thomas and Leris, they used this pendulum problem. So they gave participants this problem and then put occasional exercise breaks in between, in which they asked participants to swing their arms up and down, or to do some kind of stretching movement. And they found that those people that were swinging their arms during the break, 85% of those participants were capable of solving or coming up with a solution, whereas 62% of those who were just in the control group doing the stretching didn't find it. So although most were unaware of the explicit relationship that they're inducing here between these arm movements and the task, these hints can still be effective without any kind of conscious awareness of their task relevance. Some other important work on trying to understand how we get to a solution when we're stuck on it comes from work by Stellan Olsen, who proposed this idea of representational change theory. So when we're coming up with some sort of impasse or some sort of block to the solution, people can change the way that they represent the problem for insight to occur. So again, this is similar to the problem representation that we've talked about before. And you can do this they argued you can do this in 3 different ways. We can relax the constraints. So whatever self-imposed constraints that you've put on the search space, if we keep having problems trying to find the solution, we can relax them or think about what constraints we're putting on it. We can engage in re-encoding. So some aspects of the problem representation is reinterpreted. So how you might have reinterpreted the mutilated checkerboard problem is one. The example of the bird and the train is another of you're then re-encoding that entire representation of how you're going to go about solving it. Or finally, we might engage in elaboration. So over time, as we're stuck, you might simply think about or be exposed to new problem information. And 3 of those things together are going to combine to hopefully help us finally come up with a solution. So one example that we can see for constraint relaxation is if I give you this problem here. So you've got 9 dots on the page here. If I ask, and this is a very famous problem, if I ask you to link all 9 dots here using 4 lines or fewer, so you've got to use 4 straight lines, and the constraints that I'm going to give you is that you can't lift the pen or trace the same line more than once. So those are the conditions, and just have a think about mentally, and you can draw on your slides if you want, have a think about how you might solve that. So how might you use 4 lines to cover all of those? So again, you can't take the pen off the paper, and you can't trace over the same line more than one. Good point to pause it. So most people, when they're trying this, will generally try a range of solutions that the lines that they're sketching stay within inside the 4 dots that are appearing here. But this isn't necessarily a constraint. It's not one of the requirements that I've asked you. So the solution to this is that if you expand outside of those 4 lines, you can draw it almost like a kind of arrow box that appears on here. There's 4 lines, pen doesn't get lifted, we don't trace over the same one more than once, and it covers all 4 of those. Okay, another example that we could give of how we might need to relax the constraints sometime is some research that was done by Noblick et al. And they used sticks to present mathematical problems involving Roman numerals. So similar to this problem that's at the bottom here. So the Roman numeral for 6 equals 7 plus 1. At the moment, that is an incorrect solution. And your goal here is to try and move 1 stick to turn that solution into a true statement. So if you look at that, you've got to move 1 stick to make it true. Most people should find it pretty straightforward that you can move one of the sticks from the 7 over to the other side of the equation, and you could turn it into 7 equals 6 plus 1. So that's pretty straightforward. However, if I gave you this problem of 4 equals 3 minus 1, and I ask you to try and solve that by moving 1 stick, most people will tend to kind of scratch their head and might find this a little bit harder to solve. And the solution for this one is to change the operator. So if you move around the equals, so we're moving one of the horizontal from the equals and turning that into a minus. So now we've got the equation 4 minus 3 equals 1. So again, that's relaxing or changing the constraints that you might have proposed on the way that you could go about solving that problem. Another example, this comes from a book that I used to have as a kid. This was like a pig and a hunter problem. This hunter has fired an arrow at a pig. You've got to move 2 of those sticks, so 2 matchsticks, to be able to get the pig to dodge and avoid the arrow. One of the solutions for this is you could pop them down there so the pig ducks underneath it.